All right, let's get started. Greetings, everyone. Thanks for being in this session. I am Mayank Saxena, Senior Director of Engineering of Data Fabric Solution from MSL Samsung. We are a storage software innovation center for Samsung, especially for the flash business. We work with various sizes of companies, from Fortune 50 to startups, to understand the challenges and needs of current storage solutions and what we need to work on next, which also feeds into our product development for flash as well as software infrastructure layer for the enterprise storage, hyperscalers, as well as the end application or end customers directly. So with that background, let's dive into that. I'll briefly share the trends we see while working with the customers and the partners. What are we doing about it? What kind of solution we're working on it? And then I'll probably walk you guys through a couple of deployments of a solution, what we worked on around the high-performance object storage. So 5 years back, you could easily fit a model in a single GPU, the largest model, right? Fast forward now, the most advanced model with the trillions of parameters, you need at least hundreds, if not thousands of GPUs, right? Even the HPCs are becoming very data intensive. So what we see today is the three things applications need: scale, disaggregation, performance. Talking about scale is another aspect of the scale that these days applications, they don't care much how they access the data, but they really care what to access. They are all about objects, not about bits from the application perspective. Back then, or even today, like NFS is a perfect solution when you're talking about the small scale AI training, but it has its limitation in terms of the throughput, right? Then came the PNFS or parallel NFS, which mitigated the performance issue. So now you can have a really high performance file system, but scale is still bottlenecked on the metadata store dependency, right? So decade back, or a little more than decade back, object storage came into the picture, Amazon AWS S3, but it was mainly for the big data for the archival. But in last 1 decade or so, when you have so much data pumping into the object storage, now there's a need to basically do your queries right where the object storage is. So now it's not just a secondary or cold, it's becoming a primary storage in a lot of these applications. And that's where you start to see the innovation that now we are seeing a lot of performant object storage, which one of them is DSS, which Samsung also open source, called Disaggregated storage solution. Another aspect is a disaggregated and distributed data gravity, right? Because these days, either in distributed network or in edge, either you need to process the data, inference the information, send it back to a central server, or you need to basically gather the data as fast as possible and almost no time to your distributed server, and then inference it, right? In both the cases, the gravity matters. And based on what kind of solution you have, you need to basically filter in or use a tiering in that solution. That brings to a performance tiering, like workload flexibility versus performance, right? Normal CPUs, it's perfect for your software optimized solution, but when you need performance, then came the integrated accelerators, SIMD or crypto AI, then the discrete accelerators like GPUs, and now with the computational storage, you can do the near data processing right where the data is, right? One single tier of performance cannot serve the solution, right? So you need to have a solution which can use all the different tiering, keeping the application in mind, right? So with these three trends, there's a clear need of a solution which needs to be ground up, but should also easily be integratable with the existing deployment and solution. So serverless, kind of a serverless solution which can do the stateful and stateless computation and abstract for the application in such a way that the computational functions, where they run and physically which layer they run, it should be transparent to the user or application. So having said that, that's where the high performance object storage, what Samsung is working on, comes into the picture, and it enables the potential of the computational storage as well. So I'll basically walk you guys through two solution deployments which we worked on. On the right, you are seeing a kind of a 3 or 6 node deployment. I'll come to that why 3 or 6. But as an engineer, I'll walk you through from the bottom layer. The bottom one is the computational storage, where it has accelerator right in the smart SSD. And people who are taking picture, I promise you, in the next slide, there's a more focused picture, which will really help you. So in the drive, you can have functions offload like compression and encryption, or scan function like count queries, or encoding or decoding, right where the data is, without requiring for data to move from the storage even to the local CPU, right? Then in the middle layer, you are seeing 3 node software layer. One is the host and the target. And on the top, you have the S3 applications, which are basically S3 standard compliant. Now, in this case, you have like one use case, you can have the select query, right, issued to the system. Second one is moving average, which is very prevalent in the ML application when you have multiple layers. And the third one is showcasing the encryption. And the key takeaway is this kind of solution is for the AI and ML for the big data application when you have a true disaggregation. That is the compute, and I'll help you here. The two yellow boxes you see, one is top is the host, the bottom yellow box is the target. And they can be truly disaggregated based on the need of the application. Or they can be converged into one single node for, again, when you're just looking at the 1 node or 2 node solution, especially for the real-time analytics need. This containerization also helps in that visibility from the security standpoint. And one very important footnote, all this is possible now because of the innovation happening in the NVMe world with the performance, price point coming down. So now the performance benefit, the TCO, what we see at the edge with all this computational storage, and the target level is amplifying much more. All right, so let's, as I promised, this is a more focused picture of the previous stack. In this case, this high-performance object storage stack is used for the data analytics solution. So now in this picture, I will walk you through from the AI engineer standpoint, from top to bottom, right? If I am an AI engineer, all I basically write my applications or programs or notebook in Scala or PyTorch, stuff like that, right? And I simply rely on storage to be high throughput. Whenever my layers need the storage, the data loading needs to be fast, training needs to be fast, right? Either my notebooks can directly talk to the storage, in this case S3, or I can use notebook configuration platforms like Databricks or Snowflake, or you can have in your Hadoop cluster. All these are using standard S3 interface exposed by HPOS hosts, the middle block. The host basically consists of the object storage. We have used MinIO. We worked with them. It's a very leading open source. MinIO used to be open source. They've changed their license very recently. But we worked with them and modified their MinIO. And also now we open source our version. The whole intention was to make it disaggregated and high performant. And then the host talks to the target over the KV API, which is KV is very well suited for the object storage use cases. And that's also contributing to some of the performance gains we see. And I'll walk you through that. And on the target, the middle black box, You see the implementation of the CS API, which is a standard now as well, and then the loadable modules. In this case, you have a KV select modules, which can basically help talking to smart SSD, offloading certain function. Now on the another right arrow where you see the workflow, I don't know whether I don't have the pointer here, but the workflow API gateway is a way for applications, like especially when you have the pipeline, right? You have multiple functions. As in the previous slide, I talked about S3 select or moving average. All these can be a different function and different layers, right? So the applications can define their workload or workflow, which function to offer during which layer using the simple REST API. So that is the idea with the workflow gateway, right? And we do see a very good performance improvement for two of the use cases I'm going to talk about, in addition to TCO benefits. So let's talk about the first one. The first one we have implemented as a solution is S3 select. At this point, we have only implemented one function, but again, the idea is to showcase that it can be used for the S3 select. If some of you are not familiar with the S3 select, is the concept invented by, again, Amazon, mainly with the same thought, or in fact need, that it's pretty much the same select query like what you do in SQL, but now it's just for the S3 select, that you can query the data right in the object storage without moving the data. So that was the concept of S3 select. We have extended that further with HPOS, because now not you're offloading, you're executing the S3 select in the object storage CPU, but now we have offloaded that to computational storage, that is smart SSD itself, so that SSD itself can do the select query right where the data is or table is stored, right? So this picture basically explains how we did it. Again, the same stack. I have shown you a little bit deeper focused view. The main key takeaway is it's a stack which we have open source as well, but then we have added a loadable module, which is called the KV select, basically which you can load in the target node for this particular use case. And you implemented the select parser on the host, select executor or aggregator. By executor, I mean when you put the data, we do the chunking across all the SSDs so that each SSD has its own set of data on which it queries the select query, and the target and host aggregates the response back. And that's a huge saving because now you're not moving the data, all you're transferring even over the PCI fabric locally is just the count, right? If you're selecting a query of greater than year 1990, you're just transferring one digit instead of the whole table. So that's a huge benefit, not transferring the whole data. All right, so this is the quick, just to get a sense how exactly it compares. Like today, if you're using S3 select in the AWS, right, you have the EC2 instance querying to the AWS S3. Technically, AWS S3 is a black box for us. You query the S3. They have the CPUs on the rack, which basically hosts the S3 storage, execute the S3 select, get the response back. That's the top. The bottom is what we have on the HPOS setup, which is on-prem S3 storage. From the client side is the same thing. Client is issuing the query exactly same way, same client to AWS S3 and HPOS S3. Main difference in HPOS S3, as you can see, the query is now executing on the smart SSD, and the middle one is actually on the real load. We are working with the customer on this use case, so it's an actual customer data set we have executed against. In fact, we are showcasing this outside our booth, so I'll invite you guys to go to the Samsung table outside, and this particular use case we are actually demoing with all the video and stuff. But quickly, here are some of the numbers. I know this is a huge multiplier, 100x and 250x, so there's a caveat. It's very important to understand these numbers are dependent on your data set. If your data set is sparsely populated, you'll get a huge multiplier. If you're not, then probably not. But the key point is, with smart SSD, where you're not moving the data even like NVMe fabric as well as the PCI fabric, it does give you significant improvement in terms of throughput and latency. In this case, with this data set, the throughput here is the amount of data you have processed within the time for that particular query between S3, AWS S3 versus the HPOS. Same thing on the latency, how fast you can get your query back between the two. And one of the important key takeaways is the CPU utilization, right? If you are executing that on a standard S3, any object store, you're going to use a CPU. In this case, CPU utilization almost negligible because, again, all the query is happening at the smart SSD. Now, one other thing, it might come into the picture, hey, you are executing now on the smart SSD, not CPU, but you are using CPU processing somewhere, right? What is the real TCO? So TCO, as I said, we are not moving the data across PCI fabric. That's an important aspect. And how we measured it, the power usage of the server, right? When you execute the query without the smart SSD acceleration versus the smart SSD acceleration, with just single smart SSD, we have 4 servers. The reason we have 4 servers because that's an inherent assumption of MinIO, which requires 4 servers because of the erasure coding. But the point is, with single smart SSD, we do get 6% of power saving. And now imagine if in a large-scale system, it really amounts to a good amount of power saving. So that is the real TCO with such kind of solution. All right, so next one, I'll also walk you through the another solution we are working on called high performance video analytics. Again, it does use the HPOS stack we saw, but for a video analytics use case. So on this diagram, we are showcasing the complete solution deployment, right? Now, on the top left, you can have the videos stored on your object storage or wherever you're storing your videos, or it can be streamed from your smart cameras in either way, right? Then it goes to the HPOS servers, where we actually use a technique called iframe filtering, nothing to do with the HPOS. It's a very well-researched technique in the video AI, where we use iframe information only instead of the whole video. But the point is, when you move the data, so the HPOS solution comes with its own ecosystem, like data mover and everything. So you can customers needs to do is basically install those tools. You move the data from your video store to this HPOS, and during the put path, when you're putting the data in the smart SSDs, you are basically just doing the iframe filtering. Now, instead of storing the whole video, you still store the whole video, but you're storing just the iframes, which is good enough for the AI. And on the right side, where you want to run your video AI for all the object detection models, the 2 things happens, right? One is you either load the whole video, you decode that video, and then you basically run your models, right? So idea here is you offload the iframe filtering in the put path, as well as decoding in the read path to smart SSDs. Now with that, you're saving huge amount of bandwidth because you're not transferring the whole video file from your store all the way to the processor or application. And again, this is a software construct, so basic software-based solution. So it can be for smart SSD 1.0, 2.0, or even for 3.0 later on. All right. So just to give you a little bit more detail, what I just spoke about is on the left side, you have the traditional video pipeline, right? You have this pre-processing happening on that video file, and then the inferencing, and then the final post-processing. Again, what we have utilized is a technique called iframe filtering, and we offloaded that iframe filtering IP in smart SSD, which you see in the red. And then also the decoding IP. Right now we have the simulator IP. We are working on to offload that as well. And then the inferencing and the post-processing remain the same at the client level, at the client side. This is a quick video. Let me start with that. All right. So on the left, you have the standard video AI pipeline. On the right, you have the high-performance video analytics. The top screen is basically executing the object detection models from the application. So we are benchmarking right from the application. And the middle boxes are basically CPU utilization. And you will see on the top, video will start to load. This for the single video file, by the way. Video will start to load, and you'll see on the left, the CPU utilization is sitting around 25 to 30%, whereas on the right side, the loading is already done because it's just iframe extracted from the HPOS solution, and CPU utilization is very less. And on the bottom, you'll see the inferenced images will start to load on the destination folder. Right? So since on the right side, model is already done, inferencing already done, it's you already have the images, the inferenced images. On the left, that is still happening. So you'll see when it's finished. Should be now, yeah. So this one is done with HPVA, and on the left side, we are still happening. And the result should come up very shortly. All right, now it's done. All the inference images at the bottom screen is also done loading. And last step is pretty much the manual step. We are just displaying the image. All right. So this is just a quick comparison between the typical pipeline versus the HPVA. And again, this is the performance charts, again, contributing three major factors. One thing for iframe filtering is very important. It's, again, we are working with the customer here. For a particular solution, iframe filtering might be very good because you probably don't need really, really high accuracy. Iframe filtering does impact the accuracy a little bit, again, depending on your image resolution and stuff like that. So that's one of the techniques we have used here. So these numbers are basically because of three main factors: iframe filtering, the high performance object storage, which is disaggregated. So when you're running your model against multiple images, the large scale, it really shines because then you are utilizing multiple smart SSDs. And then smart SSD itself, because you're doing at the smart SSD. So on the top left, it's showing you the improvement with one single video file. On the top right, it's showcasing when you're running the pre-processing and the object detection on multiple files, what kind of power usage saving we see. And we have run the same experiment again, multiple files with the different resolutions. That is, different resolution means higher resolution will have more iframes, and lesser the ratio between the iframe and frames, more performance you gain. So, just to summarize, it's again against the traditional AI pipeline. It's a good improvement in terms of the performance as well as the TCO. Again, this performance improvement is because of the technique we used, but right now we are using the decoding simulator IP. Once we implement that IP in the smart SSD as well, that's when we will really get the good performance. But again, the idea here is all these different functions, when we start to utilize where it makes sense, because smart SSD might not make sense in every offloading, but especially for decoding and filtering, it will really shine, and the HPOS stack like HPOS really improves that kind of, in fact, amplifies that kind of improvement. All right, with that, I'm pretty much on my last slide. As I said, it's open sourced. Most part of it is already open source, which uses our foundational stack called Disaggregated storage solution, and we do intend to open source some of the solution I have shown here as additional loadable modules. One important thing is since we basically evolved this whole software stack while working with our customers, one other thing we ran into is how to benchmark all these things, right? When you talk about AI and you go to the AI conferences or AI community, you'll find a lot of benchmarking tools which measures the accuracy. But how do you measure that? Which kind of storage is good for which kind of AI application? Because one storage or one option might be good for one AI model, but might not be for another AI model, right? So we have developed a called AI benchmarking framework while we're working with our customers and other community, and we have open source that as well. The idea here is using that benchmarking framework, we can compare, any kind of object storage with NFS or whatnot from the AI model perspective. So AI engineers can bring their models, can bring their data set, and compare what makes sense for them. So all this is open source as part of this repository. All right, and with that, I'm done. I'll welcome any questions.
You mentioned the 100x, which I mentioned the perfect scenario in which we hit 100x. I wouldn't mind if you break down what's the, obviously, average or median, right? I'm not going to pull you to a specific number, but what is more likely to be achieved, and what are the factors that they get, say, 10x versus 100x in that performance profile?
Yeah, as I said, it's very difficult to characterize. I mean, and just to repeat the question, you are referring to the S3 Select numbers where we have shown the 100x throughput, I believe. As I said, it's very dependent on the data set. How sparsely you are populated and which column you're querying against, all these things. We have seen from 20x, 10x to all the way to 500x. If your data set is like pretty much empty and only very sparsely populated. So to answer your question, again, very data set specific. That's why, like, if you have a large data set, general thing is if you have a large data set, you will see a good performance. Because then not only single smart SSD, the disaggregated and the aggregated result amplifies this whole thing. Then you get more throughput. And if you have small data set and you're just using one single smart SSD, probably not. So that's a general guideline, but I don't think anyone can put the number.
No, fair. Would it also depend on the periodicity of updates and performance over time? Changes in the way it's stored and moved and potentially compacted and such?
Oh yeah, that's a very good point. So all these numbers were on a data at rest, so it was not modified during the runs, right? Because one important thing is when you're putting this data, it's chunked and tagged, right? So every time you're updating, the numbers might be different because you're updating the data set itself. So that's during the put path, all this chunking happens. So yeah, that's an extra step, but not a huge overhead as we have measured. Because again, as I said, it really shines when you have a large scale data set and you have bigger object size. If you have a smaller object size, let's say if you're talking about KBs of data set in general, not just solution, object storage, because of the erasure coding, probably not a right solution. But because in this age of AI and big data, when the object size is increasing, your data set is increasing, that's where all these solutions are making much more sense now. All right. Any other questions?
Does the number of objects, regardless of the size, play a role in the performance?
No. Again, it's a function of how big is your system, right? You can number of object will, but then it might be tunable in terms of because then in the smart SSD we can have multiple kernels. Then you can tune how many IPs you can run at the same time. It will, but again, you can design accordingly based on your number of objects and stuff. Because just to give a reference, we have tested the system. This system was actually evolved or basically came into foray for petabyte of scale of data set. So you can imagine what kind of customers we are working with. So a number of objects you can easily imagine the kind of number of objects. So, and the throughput is, I mean, it's With NFS systems for customer, it was really bottleneck because then the number of objects comes into picture because then your metadata store is also very high and then the whole thing, the whole throughput sacrifice. But with object storage, number of objects, because then we keep adding the more cluster object storage and generally throughput should scale linearly.
The solution you mentioned was in the picture enterprise key value store under the min.io.
Mm-hmm.
Yeah,
so we have key value store. So min.io is object storage, right? We basically worked with them to modify for the KV. A KV API is something Samsung has implemented, and it's compliant to the KV standard. So that is basically baked into that host software and target software. So that, and also that helps because the semantic from object to KV, it's very efficient versus just the block.
But the standard min.io is actually writing to a file system.
Correct, writing to block. Right. And we have this KV. So again, by the way, right now, since we don't have a KV SSD, we are also converting to a block. So we have this ROXDB layer, which we convert. So that's kind of overhead for us. But we have designed such a way that when we have this KV semantic implemented all the way to the flash, then we just take the whole conversion layer out as well. And then this will further improve the performance. But right now, between the host and target, that is the KV over NVMe over fabric versus the block. Yeah. All right. If no more questions, thank you for your time. Thanks.